Today I'll prove the theorem of Chevalier-Weil. First I'll give two equivalent formulations. So the first formulation is KB a number field and S a finite set places containing Archimedean ones. It's C1 smooth algebraic curves defined over K. They might be projective or affine. And phi is ramified over defined over K. Now, there exists a number field prime set of places is prime, which is finite, such that S prime contains all the places above 12 of S, and such that every rational point, every integral point, S integral point, S2 admits a preimage which is S prime integral. So there exists P prime in preimage of P. Prime S prime integral points of C2. I give the second version. So, under the same hypothesis, there exists finitely many curves to 1 to n defined over K, and morphism by I from C to I to C1 such that well, the first thing is that for I different from J, I, J are index indexes between 1 and n. There exists an isomorphism psi ij C2i C2j. Find over the algebraic closure, making diagram mute. This is J. And moreover, C21 is isomorphic with C2, and phi1 is equal to phi. And second thing is that for each integral point C1, there exists at least one index I, 1 to n, such that the preimage contains S integral point. So these curves are called twisted curves. They are all isomorphic over the complex numbers, but not necessarily over K. And actually, I'll be interested in the first version. It is easy to pass from one to the other. And actually, as I said last time, in order to apply Schiaparelli-Weil theorem in the proof of Siegel theorem, it is sufficient to restrict our attention to very particular cases of these curves. Over the complex, it's just C2, but over K, they are not necessarily isomorphic. Oh, just if you want an example, if you take C1 equal to C2 equal GM, and you take the co-ascending x to x squared, or you take the co-ascending x to twice times x squared, you can take, for instance, C2 1 and C2 2. You can take both equal to GM, but there will not exist such a commutative diagram over Q. But over Q square root of 2, you can make a change of variable. So actually, we just need to consider very special cases of covers, and for simplicity, I restrict to abelian covers, and the case of abelian covers reduces further to the case of cyclic covers of prime order. So I just something about cyclic covers in general. we fix a prime L. We suppose the number field K contains all L roots of unity. Now, if we have a cover defined over K and Galois over K with Galois group isomorphic Z modulo LZ, then this means that the function field K of C prime can be viewed as an extension of A of C, and precisely it contains the field phi star of K of C. This is a Galois extension with Galois group Z modulo LZ. So by Kummer theory, we have that A of C prime equals K of C L root of F, where is a rational function and not a perfect L power in K of C. And vice versa, given F, you see, not a perfect L power, we can construct a C prime in this way. We first define the open curve C star equals C minus zeros and poles F, and then let C star prime be the set of points E lambda, such that lambda dn is f of P, and well, P lambda of course is P. And this is a curve endowed with a map with a projection to C, sending P lambda to the point P, and C prime will be the completion of C star prime. Now the cover phi is unramified if and only if F is locally Lth power everywhere, which is equivalent to saying that F has all zeros and poles of multiplicity divisible by So one can in this way classify the unramified cyclic cover of degree L by considering the set of rational functions such that f is f power locally everywhere. This is actually consider not identically zero functions. This is a group made the quotient by subgroup of functions of the form g to the L. G is in case star. So modulo those who are globally as power, and this is a finite group. One could call it H1 Z modulo LZ. It is a finite dimension vector space over Z modulo L, which is the finite field with L elements, and its dimension is equal to twice the genus if C is complete, and it's twice the genus plus R minus 1 if C has R points at infinity. Sorry. Complete curves minus R points. Now, before giving the proof of Chevalier-Weil theorem, I'd like to show concrete examples. Last time I started with an example using an elliptic curve. Now I take the more general equation for an elliptic curve. Consider y squared equals x minus 1, x minus lambda. And to simplify, we work over the integers. And lambda will be different 0 and 1 if you want the curve to be smooth. Actually, we're interested in compact curve. That's y squared equals squared x minus z, x minus lambda z. So I noticed last time that the function small x, which is capital X over z, is locally a square everywhere. So if I call this E, this curve, so the field extension obtained by adding to the rational functions on E the square root of x will be unramified over Q of E. So this function field corresponds to another curve and the morphism to E. And this morphism will be unramified since the X is locally square everywhere. And by Chevalier-Weil theorem, I expect that there exists number field containing all square roots of X or XY ranging over the rational points of Q. So write X1 is A over D, B over D, where D is a minimal common denominator, which means that no prime at the same time. And I'd like to prove that apart from finitely many primes, which will be found explicitly, each prime will divide the rational number A over D an even number of times. So either it divides only A with even multiplicity, or only D with even multiplicity, or both A and D in such a way that after simplification there will remain an even multiplicity. So with the same parity of the multiplicity. And we write the equation, so it is A square A over D minus 1, A over D minus lambda, multiplied by D cubed, so P squared D equals A minus D, A minus lambda D. Now, take a prime P. Let P be a prime, not dividing lambda multiplied by 1 minus lambda. Note that lambda is different from 0 and 1, so that this number is non-zero. So there exist only finitely many primes dividing product. So what I'm going to say holds for all but finitely many primes. Now suppose first that P divides A and P does not divide D. So taking the periodic valuation, we have nu P B squared D equals twice nu P of P. This should be equal to, so P does not divide D, so it divides A minus D with the same multiplicity with which it divides A, and the same here. So here we obtain 3 times nu P of A. So I obtain that nu P of A is even. Nu P of D equals 0, so nu P of A over D is even, as wanted. Now, suppose that P divides D and P does not divide A, so So this is impossible because P divides d squared d, while A minus d, A minus lambda d is congruent to A cubed mod P. So it's not congruent to 0 mod P. So this is possible due to this equality. And then suppose P divides A and P divides D. And here I like to distinguish two subcases. So first subcase is that they have distinct multiplicity. So note that in this case, P does not divide B because no prime divides all the three. So here we have nu P of D, which is equal to nu P of A plus, and each of these terms is divisible by P to the minimal powers dividing 2. So twice the minimum of nu P A, nu P of D. And this is an even number, so nu P of D is congruent to nu P of A modulo 2. And so nu P of the quotient A over D is congruent to 0 modulo 2. And last case, P divides A and P divides D, and they have the same multiplicity. This case is impossible because on the left side I have nu P of D. Again, P cannot divide B now, so here the multiplicity is this one, and this should be equal to nu P of A, which is the same as nu P of D, plus something which is strictly positive. So it is impossible. So finally we obtain that that so the Q square root x over Q, or x A over D, is unramified outside the primes dividing the 1 minus lambda, and possibly the primes 2, because you know that primes 2 sometimes ramifies quadratic extensions in Q of I as Q square root of minus 1 ramifies. So square root of x belongs to the field generated by square root of minus 1 divides lambda 1 minus lambda, and this is a finite degree extension of Q. And the idea of the proof of Valuation theorem is the same. No. This work for rational points because it is unramified over the I mean, even at infinity. So there is no S. There is no S. It works for rational points, and these primes are those giving their square root give the field K prime. So I cannot say that the pre-image are in Q, but they are in a field K prime. Now to prove well, we prove Chevalier-Weil first in the compact case. So there is no S, and the ring of S integers is. It should work for all rational points. So the curve in question now are complete. And here, prove that the f of p, so p varying in the set of rational points, does not ramify outside a fixed finite set of primes of OK independent of which means that nu of f of p is congruent to 0 modulo f for all places nu outside fixed finite set. Now, to do this, f of p is a scalar in K, and nu is a place of K. Yes, f is fixed. So in our theorem, f is fixed because f depends on C2. And we have to find a finite set of primes depending on f, such that for all rational points p, and all nu outside this finite set, nu of f of p is divisible by L. In the preceding example, f was the function x. And first of all, working with the f minus 1 instead of f, it suffices to consider the case if so I have to prove that for every point p such that nu of f is positive, this number is divisible by L. Now, pardon? L is the L appearing in here I have, this is a cyclic cover of degree L. So I said that I will prove Chevalier-Weil theorem only in this case. And it is unramified. Which means, as I said, that function field of S2 is obtained by extracting an Lth root of a function f, which is locally everywhere a perfect Lth power. Now, I have the right of enlarging the field of definition K by taking a finite extension. So I enlarge all zeros of f are K ratio. Now, we can consider the open curve C minus the set of now C can be embedded in an affine space AM, and here it is defined equations with rational coefficients. Now I consider a finite set of places with respect to which sum of this coefficient is not integral. So pardon? Every curve minus a non-empty set is affine. So since f is non-constant, it must have some poles. And if I eliminate these poles, the complement is isomorphic to a closed subset of AM. Basically, by a Riemann-Roch theorem, you can find many functions having poles only in the set of poles of f and constructing embedding into AM. Now, you can take S, finite set of places, that coefficient of the equations of C are S integral. I repeat that I'm interested in all rational points and not S integral points. This set will be the set of places outside of which this condition can be proved. But it will be proved for all rational points. Actually, in the sequel of the proof, I will enlarge again S. Now, I need the following lemma. 1. For all but finitely many places outside S, zeros, the reduction F modulo the maximal ideal are just zeros, are just the reduction of the zeros of F. I'll explain a little bit this statement. So the curve C is defined by certain equations in m variables. The function f being regular on C, because we eliminated, this is C minus with star. This is C star. So f is regular on C star, and so it is given by Hilbert-Nussdalen-Satz by a polynomial in m variable x1, x2. So we can reduce modulo prime the equations for the curve and the polynomial defining f, and so we obtain first a curve defined over a finite field and another function defined on this field. Of course, if you have a zero of f which is rational, you can reduce this the coordinates modulo nu for all but finitely places nu, because for some places it means that some denominator of the coordinates of 0 of f is in the maximal ideal, so you cannot reduce. But for all but finitely many places, it makes sense to reduce the 0 of f modulo this place, and you obtain, of course, a 0 of the reduced f. But in principle, there might be some more zeros. And actually, this is not the case. Consider, for example, a particular case m equals 2. So you have a curve defined by g of xy equals 0. This is the equation of star. And then you have f of x6. So f is equal to a certain polynomial xy. So the zeros g, since this curve is irreducible, this system has only finitely many solutions. So if you take the resultant, so call a of y resultant with respect to x of fg, and for b of x the resultant with respect to y of g, then a of y and b of x are not identically 0. So the coordinates xy of the zeros of f on C must satisfy the equation b of x equals 0, a of y equals 0. And each equation has only a finite number of possibilities. When you reduce modulo some prime, it might be that one of these polynomials is identically 0 because all coefficients belong to maximal ideal. But for all but finitely many places, the reduced polynomial will still be non-identically 0, so they will have just finitely many solutions. And now by Bézout's theorem, if there are only finitely many solutions, these solutions, the number of solutions is what you expect. And actually, this argument can be generalized to arbitrary m. There are several ways. Either you consider a more complicated ideal giving the equation of C star in a higher dimensional affine space, and the theory of resultant can be extended, or simply you notice that each curve can be covered by a finite number of affine open sets, each of which can be embedded in A2. So you have a finite number of reasoning of this type, and each time you have to consider some bad primes. So consider a second lemma. So there exists, or for all but finitely many places of A, the following holds. So let P be a rational point such that mu f of P is positive. So there exists a rational zero U C K of F such that P is congruent to Q modulo maximal ideal associated with the place, and also if H is the order of F Q, and suppose that P is congruent to Q modulo the kth power of the maximal ideal and not modulo k plus first power, then mu f of P will be precisely equal to the product K. This is the key lemma. This is what we used in the example of the elliptic curves, when we said that we remarked that in the example small x is as double zero at 0, 0. So we had to estimate nu of x calculating a over d, which a over d, b over d, which means nu of a over d. Remark that when p divides a not d, then a over d is congruent. Well, the pair a over d, b over d is congruent to 0, 0 modulo a certain power p. Then the value was then the values nu p was twice that. So yes, okay. So to prove this this lemma, well, the first part is is contained in the lemma 1. So if nu p of p is positive, this means that p is a 0 for reduction of f modulo mu. So p is the reduction so the reduction of p coincides with the reduction of a 0 q. Now we choose coordinate. That q is the point with is the origin in AM. So after a linear change of coordinates, we can suppose that the first coordinate is a local parameter at the origin. X1 is a local parameter. And n analytic function is 1. So locally in the origin, can use x1 as a coordinate, and all others can be obtained by implicit function theorem in terms of x1. Since This is a smooth point of a variety of dimension 1. Now, F as order h at the origin means that f is of the form x1 to the h multiplied by a non-vanishing in a neighborhood of u. So this means it is a rational function where a0, a the origin not 0 and b the origin is not 0. So a0 over b of 0 is in k star, and so enlarging s a of 0 over b of 0 becomes an S unit. So I mean that I put in S all the primes dividing numerator denominator p. So now if I calculate f of e, this is equal to x1 of p dh by e over d. And now since p and q are congruent, since modulo the maximal ideal, so I obtain that is equal to h times mu x1 t, and this is 0. So for all new, provided nu does not belong to S, this enlarged set S, and now x1 of p nu of x1 of p actually is this number k, because the local parameter, the new order of the local parameter gives the new distance from p and the origin. But actually what I really need is that this value is congruent to 0 modulo h. So this is the corollary of lemma 2, or which I need. So so now the proof is finished. So we've proved that there exists S finite such that for all nu not in S will be such that nu of f of p is positive. We have nu of f of p is congruent to 0 modulo some multiplicities, but all the multiplicities are divisible by L because f was locally a perfect L power everywhere. So this is congruent to 0 modulo L. And as I said at the beginning, replacing f by f to the minus 1, this also holds when nu of f of p is negative. When it is 0, no problem, because 0 is congruent to 0 modulo L. So finally, the field K is equal to P, for P varying over all points, all rational points. This ramifies only over finitely many places. And this proves that it is a finite extension of K. Okay. Now, what should we change in the open case? In the case the curves were not complete. Open case. So C now is a C tilde minus a certain finite set. This is actually C1, and so C2 is a C2 tilde minus well, finitely many points. So the hypothesis is that the cover pi is unramified. I can certainly, this is 2, this is 1, certainly embed curves, their completion, and extend the pi to a cover of completed curve. But now this pi might be ramified, pi tilde might be ramified over Q1, QR. Because the hypothesis was that this cover was unramified. So in this means that F might have poles or zeros of multiplicity not divisible by L at Q1, QR. So all zeros and poles, but possibly those in QR, 1 QR, if some of this point is a zero or a pole of F, have multiplicity multiple of L. And here we don't know. So everything applies. This lemma is still true. We will not use any hypothesis on F. But in order to finish the proof, we must control the case when P is congruent to a Q, which is in this set here, Q1, QR. In that case, we cannot say that H is multiple of L. But if we restrict to S integral points, which means with respect to, well, actually I call this SD integral points with D, the divisor, Q1 plus QR. So we restrict precisely to those points which never reduce modulo a point in Q1, QR to a point in Q1, QR modulo any place outside S. So for these points the proof works, and so it gives the result for integral points. So again, the example of GM is illuminating. GM to GM compactify as P1. Take x to x squared. So said GM of OS are just S units. So take a square root of an S unit. There is no ramification outside S. But if you take an arbitrary rational point in GM, we can have ramification. We have ramification precisely when this point reduces to 0 or to infinity. This is GM plus 0 infinity. If you take a rational point x, call it A over B, when P divides A and not B, it means that x reduces to 0 modulo P, and by taking square root, P might ramify. And the same if P divides B, it means that x reduces to infinity, and so by taking square root, it ramifies. But if x is supposed not to reduce to 0 infinity, so A, B have no primes outside S, then there is no ramification outside S. Okay. Now I'd like to give application. So there was classical proof due to Siegel of a particular case of a theorem for hyperelliptic curves. He proved that the equation y squared equals f of x, where f of x is polynomial with no repeated factors over complex number of degree at least 3, has only finitely many solutions x, y. So this is a particular case of what I call Siegel theorem, which applies to all curves of positive genus, but which was proved before, a few years before the general case. And the idea was to reduce to S-unit equations. The idea was that we factor f as constant x minus alpha 1, x minus alpha d. D is at least 3, and alpha I is distinct from alpha j for I distinct from j. Now consider S finite set of places of Q alpha 1 alpha d such that A is an S unit and the alpha I are all S integers. So each solution of this equation, for each solution xy, we have a curve x minus alpha 1, x minus alpha d are all S integers, and this product is a square. So we have that the ideal x minus alpha I have well, so are of the form a certain ideal E multiplied by J square, where I has only finitely many possibilities. This is because the product is a square, and if two elements belong to a same ideal, then the difference, which is alpha I minus alpha j, should belong to this ideal. Actually, if one enlarges so that alpha I minus alpha j for I different from j are all S units, then no two distinct elements can belong to the same ideal. So if the product is a square, it means that each term is a square. Okay. So that I disappears after enlarging. Yes. So enlarging S again. You can suppose that OS is a principal ideal domain So if the ideal is a square, then x minus alpha I will be a square times a unit. Okay. And enlarging k, you can suppose that all the units in the previous field are squares. So can achieve x minus alpha I equals beta I square. Okay. So now we have that. So we take 3. So now we can make, well, it's the usual trick. We have 3 terms which depend only on one variable, so there must be some relations among them. So we eliminate x to distinct ways. So beta 1 square minus beta 2 square equals alpha 2 minus alpha 1. So here, for instance, we have beta 3 square minus beta 1 square equals alpha 3 minus alpha 1. So we can factor here beta 1 minus beta 2 multiplied by beta 1 plus beta 2 equals alpha 2 minus alpha 1, which we said is a unit. And here saying plus beta 1 is alpha 3 minus alpha 1, which is another unit. So finally, each of these 4 terms is a unit. So we have that beta 1 minus beta 2, this u1 is a unit, and beta 1 plus beta 2. And here we have beta 3 minus beta 1 is also a unit, and beta 3 plus beta 1 is again a unit. So all these are units. And now again we have that these 4 terms u1, u2, u3, u4 are depend on only 3 parameters, beta 1, beta 2, beta 3, so there must be a linear relation. And moreover, we have other relations which are u1, u2 equals a constant, and u3, u4 equals another constant, which is alpha 3 minus alpha 1. So actually we can write in terms of just 2 units, u1, u3, and these two units satisfy a linear relation. So actually u1 minus 1, u3 minus 1 satisfy okay, I don't write exactly the linear relation, but just to give the geometrical interpretation of this construction. Well, first of all, what we obtain a map. So we obtain two units u1, u3 satisfying an algebraic relation, and we view u1 and u2 as functions. In u1, u2 are functions of it can be expressed as in terms of beta, and the beta can be expressed in terms of algebraic functions of x. So beta 1 is a square root of x minus alpha 1, and so on. u1, u3 are algebraic functions on the curve y square equals f of x, which called C this curve. Algebraic, but not a rational function, because the betas are obtained by taking square roots. So it means that they are rational functions on another curve which dominates C. So we have a cover. So C prime, as the function field of C prime is obtained from the function field of C by adding the square roots of x minus alpha 1, x minus alpha 2, x minus alpha 3. And in u1, u3 can be viewed as regular functions on C prime. Algebraic function on C, so regular function on C prime. And they give a map to gm square, because they are never vanishing, and the image is contained in a certain curve, and the equation for this curve is the algebraic relation which is obtained from here, eliminating the betas. So we obtain geometrically we obtain this map, and from an arithmetic point of view, we have that each integral points here gives rise to an integral points here, provided that we consider a larger field and a larger set S, because in this reasoning we have enlarged several times S and even the function, the number field of K. So after enlarging K and S, we can say that each integral points on C gives rise to an integral point on C prime, and then to an integral points in gm square which lies on a certain curve, and to this curve we apply the S-unit equation theorem that we saw, and so using the S-unit equation theorem we can provide finiteness of solution to C. There is no map, no non-trivial map from C to gm square, because C has not enough points at infinity. Maps from C to gm are given by functions having all their zeros and poles at infinity. And it is not possible to find interesting maps from C to gm square, but after taking a cover, it is possible. So implicitly, Siegel used Chevalley-Weyl theorem here, and yes, unit equation theorem to in GM square. Okay, so I stop here for today.